Hello, I'm Liam Hills, and in this short video I'll be responding to the questions on my final year project for my renewable energy engineering degree. The UK government recently pledged that offshore wind farms will generate enough electricity to power every home in the UK by 2030. With such a reliance forecast on wind power, its reliability is paramount. Initial research revealed that blades were the most likely component to fail out of a horizontal axis wind turbine and corresponded with the most downtime. The project focused on reducing the likelihood of fatigue, a leading cause of blade failure, by varying the blade's aerodynamic design. The project aimed to investigate the effects of changing the geometric properties of the blade aerofoils on the aerodynamic forces experienced, minimizing the forces which contribute to fatigue without contributing to power output should help reduce the likelihood of blade failure by fatigue while maintaining a high turbine power coefficient. The thrust force, or normal force, acts on the blade trying to bend it backwards towards the tower. It doesn't contribute to power output and tends to be much larger than the useful tangential forces which are responsible for torques. Blade element momentum theory was used to estimate the aerodynamic forces which the blade would experience. There were designs which had significantly lower forces and would therefore be much less susceptible to fatigue. However, it also corresponded with a large reduction in power output. These designs may be suitable if reliability of power was a priority. However, energy companies may favour the overall profitability of a turbine, and therefore the solutions may not be commercially viable. The biggest challenge to the project was selecting which design performed the best. The ratio of power output to thrust force was very similar for all the designs and couldn't really be used as a measure of design success. If scale models of each design could be made, the forces that were calculated over the range of simulated wind conditions could be converted into stress cycles. These could be run, given more accurate estimates for the lifespan of each design. And once this was known, then the estimated lifetime power of each design could be calculated before fatigue occurred. And this would be a much better, more accurate measure of which design performed the best. The most interesting part of my project was using the program Xfoil to analyse the airflow around the different airfoils. The program was unfamiliar to me before I started this project, and experimenting with the different commands and getting to grips with the software was quite an enjoyable experience. Being able to visualise the boundary layer separation, how that began to occur with increasing angles of attack was interesting, and was also useful for the project in finding which angle had the highest lift coefficient to drag coefficient ratio. Thank you.